And today I bring you a super interesting problem about gravitational fields. Not only will you understand it perfectly, but you will also learn how to calculate the gravitational field, the gravitational potential, the gravitational force, and the gravitational potential energy at a given point. Welcome to Binnacle Project.
Binnacle Project.
I wanted to give you this exercise because we are dealing with the four most important magnitudes in gravitation. And like always, let's read together the statement. It says, 3-point masses A, B, and C with values Ma 5 kilograms, Mb 10 kilograms, and Mc 20 kilograms are placed at the points 0, 0, 4, 0, and 0, 3 meters on the plane respectively. Section A says, calculate the gravitational field at point 43. Section B says, calculate the gravitational potential at that point. Section C, if a fourth mass of 2 kilograms is placed at point 43, calculate the gravitational force it experiences. And Section D, calculate the gravitational potential energy of that mass. And we are given as data the universal gravitational constant. So let's get to it. The first thing we're going to do, of course, is to draw the situation. And if you read carefully the statement, you will notice that the action happens in the first quadrant of the Cartesian plane. That is, at point 0, 0, they are placing the first mass of 5 kilograms. At point 4, 0, 1, 2, 3, 4, at this point, they are placing the second mass, Mb 10 kilograms. And at point 0, 3, that is on the y-axis, they are placing the third mass, that is Mc 20 kilograms. And the first thing they are asking us to calculate is the gravitational field at this point, at point 4, 3. 4, 3. So in the next few minutes, we are working here. Pay attention to the first two sections because we are calculating the gravitational field at point P and the gravitational potential at the same point. And even though there is no mass at point P, we will be able to calculate these two quantities. So that's the first thing you should learn, that gravitational field and gravitational potential can be calculated without the need for a mass to be here. But on the other hand, sections C and D, we are placing a test mass at this point, and only in that case we will be able to calculate the gravitational force and the gravitational potential energy that this mass will suffer. Having said that, let's get to it. We begin by calculating the gravitational field at point P, and to do that we are applying something called the superposition principle, which means that the final gravitational field at point P will be the sum of the gravitational fields created by these masses. So first of all, think that we are alone with mass A, and please forget masses C and B, okay? Having said that, the first step number one, step one, we are creating this vector, a vector that originates at point P, 4, 3, and ends at this point, point A, 0, 0. It is very important to create properly this vector, PA. And as you can see from this little symbol, the origin of this vector is point P, and it finishes at point A, okay? And now let's create that vector. The sequence is always the head minus the origin. This is the sequence, the head minus the origin. That is A minus P. 0, 0 minus 4, 3. And our vector is going to be -4, -3. This is the first step. Step number 2. we are creating a unit vector with the same direction and orientation as PA. Look, let me draw it for you. We are creating this little vector that has the same direction and orientation as PA, but its modulus is 1. That's why we are representing it with U sub A, because it's pointing to point A. And this little symbol means unit vector, right? This is step number 2. Step 2, create U sub A. And how are we doing it? Just by dividing. Look, if you want a unit vector with a determinate direction and orientation as other one, just divide vector PA by its modulus. Vector PA divided by its own modulus. And can you guess the formula for the modulus of a vector? I'm sure you already know it. The modulus of a vector is the square root of each of its coordinates squared, okay? Each one of its coordinates, but squared. That is -4 squared, but as it will become positive, I'm just writing 4 squared, plus -3 squared, but in positive because it's becoming a positive number. And there we have the modulus of our vector PA. 16 plus 9 is 25. The square root is 5 units, is the magnitude of this vector. So there comes vector U sub A, -4, -3 divided by 5. And here we have our vector U sub A, that is -4 fifths and -3 fifths. Second step complete. Step 3. Now we're calculating the gravitational field caused by this mass at point P. Okay? We are calculating the gravitational field caused by mass A at point P. That will be step number 3. We're calculating the gravitational field, but only in magnitude. Don't worry about the direction and orientation because it will be obtained at step number 4 thanks to this vector. Now we are calculating only the gravitational field, but in magnitude. And how do we do it? Just by using Newton's gravitational law. You know, G multiplying creating mass divided by distance squared. Distance squared. And we are doing 6.67 times 10 to the negative 11 multiplying creating mass 5 kilograms divided by distance squared. This distance but squared. And how are we calculating this distance? Naturally, using the Pythagorean theorem, which says that hypotenuse squared equals leg square, 4 square, plus the other leg, but also squared, 3 squared. This expression gives us 16 plus 9, 25. And wow, we are lucky, because the Pythagorean theorem gives us the distance already squared. So let's place here our 25. And now it's time to use the calculator. If you did it carefully, hope you obtained 1.33 times 10 to the negative 11 newtons per kilogram. And now it's time to finish our calculations by calculating the gravitational field, but in form of vector. This will be step number 4. The gravitational field created by mass A, but in form of vector, will be this magnitude, 1.33 times 10 to the negative 11, multiplied by this unit vector that we calculated at step number 2. -4 fifths, -3 fifths. And we will obtain the gravitational field created by mass A at point P. If you did it carefully with your calculator, hope you obtain 1.33 times 10 to the negative 11 multiplied by negative 4/5 have you obtained negative 1.07 times 10 to the negative 11, and here we are using the physical notation instead of the mathematical notation. And as this is the first coordinate, the horizontal coordinate, we are using vector I as unit vector. Okay? This is the physical notation, which is better for the subject. And on the other hand, if you do 1.33 times 10 to the negative 11 multiplied by negative 3/5, have you obtained negative 7.98 times 10 to the negative 12. And as this is the second coordinate, vertical coordinate, we are using J as unit vector. And here we have the first gravitational field caused by mass A. As you can see, I've erased the previous calculations in order to have a space for calculating gravitational field caused by mass B and gravitational field caused by mass C. Don't forget that we are applying the superposition principle, which means that the final gravitational field at a point will be the sum of the gravitational fields created by each masses. So now let's proceed with gravitational field caused by mass B. And we are doing the same. Look, step number 1. Step 1, we are create vector PB, that is a vector with its origin at point P and its end at point B. Create PB. And don't forget that it is very important to do the end, point B, minus the origin, point P. That is point B, 4, 0, minus point P, 4, 3. And we are obtaining 4 minus 4, 0, 0 minus 3, negative 3. Here we have our first step. There comes step number 2, where we are creating a unit vector, this little one, unit vector, that has the same orientation as PB, but with modulus 1. This will be step number 2. Create this unit vector, U sub B. And how are we doing? This is the symbol for unit vectors. How are we going to do it? Just by dividing vector PB by its modulus, its magnitude. And you can see it's not necessary to use the square root because the modulus, the magnitude of this vector, is naturally 3. The distance are in meters, so this vector has magnitude 3. So let's divide 0, negative 3 by 3. And we are obtaining 0 and negative 1. This is our unit vector pointing towards point B. And now there comes step number 3, where we are calculating the magnitude of the gravitational field created by mass B at point P. In magnitude, don't forget that it's not necessary to use the negative sign of the orientation, etc., because we will obtaining this data at step number 4 thanks to this unit vector, just in magnitude. And we are using Newton's gravitational law, G multiplying the creating mass divided by the distance squared, this distance. Let's say that it is 6.67 times 10 to the negative 11, multiplying the creating mass, 10 kilograms in this case, divided by this distance squared. And as we were telling, this distance is 3 meters, so 3 squared, 9. And now it's time to use the calculator. If you did it carefully, hope you obtain 7.41 times 10 to the negative 11. And now there comes step number 4, where we are presenting the gravitational field at point P caused by mass B, but in vector form, in vectorial form. G sub B vector will be this magnitude, 7.41 times 10 to the negative 11 multiplied by the unit vector that we prepared at step number 2, 0, negative 1. 0, negative 1. And it's time to multiply this magnitude times 0, 0. There is no horizontal component. And this magnitude multiplied by negative 1 will be negative 7.41 times 10 to the negative 11. And using the physical notation, as this is the second magnitude, the vectorial magnitude, we are using J as unit vector. And of course, don't forget the units, please. Newtons per kilogram. And this is the gravitational field caused by mass B at point P. Here you have the two gravitational fields that we have already calculated. And now, of course, it's time to calculate the last one, the gravitational field caused by mass C at point P. And you know, we are proceeding the same way. Step number 1, let's create vector PC. Don't forget that it's very important to have its origin at point P and its end at point C. This is vector PC, and we are doing the end minus the origin. That is point C, 0, 3, minus point P, 4, 3. And we are obtaining 0 minus 4, negative 4, and 3 minus 3, 0. This is vector PC. Step number 2. Step 2, let's create the unit vector pointing towards point C. This little vector that has the same direction and orientation as PC, but with modulus 1, U sub C. We are creating it as vector PC. Let me present you the expression. PC divided as always by its modulus. Okay? And let's do negative 4, 0 divided by the modulus of PC. And it's not necessary to use the square root because you can see that the modulus, the length of this vector, of this arrow, is naturally 4. 4, okay? So our unit vector, our unit vector will be negative 4 divided by 4 will be negative 1 and 0. This is the step number 2. Now it's time to calculate the magnitude of the gravitational field caused by mass C at point P. This will be step number 3. And we are calculating it, as I told you previously, in magnitude, only in magnitude. And we are using Newton's gravitational law. G multiplying creating mass divided by distance squared. We are doing 6.67 times 10 to the negative 11 multiplied by creating mass, 20 kilograms, divided by distance squared, 4 squared, that is 16. And as always, it's time to use our calculator. If you did it carefully, hope you obtain 8.34 times 10 to the negative 11 newtons per kilogram. And there comes the last step, step number 4, where we are calculating the gravitational field at point P caused by mass C just by multiplying in vectorial form, just by multiplying this magnitude, 8.34 times 10 to the negative 11, multiplied by the unit vector that we built at step number 2, negative 1, 0. And we are presenting the solution in the physical form. This number multiplied by negative 1 will be negative 8.34 times 10 to the negative 11. And as this is the first magnitude, the horizontal magnitude, we are using the unit vector I. And of course, that is the units. Newtons per kilogram. And now we are ready to calculate the final result. Now that we have already obtained the gravitational fields caused by each one of these masses at point P, it's time to add them up in order to obtain the final gravitational field. It will be G sub P, the gravitational field at the point they are asking us to calculate this gravitational field. And we just have to add these magnitudes. We can do it together, so please take your calculator in order to do. First of all, let's add our horizontal magnitudes. That will be negative 1.07 times 10 to the negative 11 plus negative 8.34 times 10 to the negative 11. Please do it with me. It's very important for you to train with your calculator. Hope you obtained negative 9.41 times to the negative 11 I. Okay? This will be the horizontal magnitude. Let's clear our calculator in order to do negative 7.98 times 10 to the negative 12 minus 7.41 times to the negative 11. Hope you obtain negative 8.21 times 10 to the negative 11 J. And of course the units, newtons per kilogram. This is the final result. As this is the horizontal component, let me call it G sub x. And as this is the vertical component, let me call it G sub y. But it would also be very interesting to present the solution in the form of modulus. Just we are calculating the modulus of G sub p by using the square root of gx squared plus gy squared. And that will be also another way of presenting the final result, but this one is more complete. If you did it carefully, hope you obtained 1.25 times 10 to the negative 10 newtons per kilogram, and we have already finished section A. Now it's time to calculate the potential at point P.
Binnacle project.
Now that we have already calculated the gravitational field at point P, not only in vectorial form but also in magnitude, it's time to solve section B, where they're asking us to calculate the gravitational potential at point P. The gravitational potential, which is represented by V sub P. And good news, even though the gravitational field is a vectorial magnitude, the gravitational potential is a scalar quantity, is a scalar magnitude, so we won't have to deal with the vectorial treatment that we had to use at section A. Okay? Second, you can see that there is no mass at point P. There is no mass at point P. It's only a point floating in the space. But only for the presence of other masses around, automatically appears a gravitational potential. Right? And the last one. We are using, again, the superposition principle, which means that the final gravitational potential will be the sum of the gravitational potentials created by each one of these masses. The gravitational potential at point P will be the one created by mass A plus the one created by mass B plus the one created by mass C. Ready? And which one will be the expression, the mathematical expression that we are using to calculate these potentials? This one. The potential at a point equals negative G multiplying the creating mass divided by the distance, not distance squared, only the distance. And the units, of course, are joules per kilogram. You have access to all these formulas in the PDF that I leave you in the description. It is very important for you to know the meaning of the different magnitudes you are working with in physics. And what does the gravitational potential mean? This is the work that must be done to move 1 kilogram of mass from a point to the infinite. Okay? Imagine that we have here a creating mass and we are calculating the gravitational potential at this point. So the gravitational potential is the work that must be done to move 1 kilogram of mass from this point to the infinite. And considering that masses are attractive, you will have to do this work because the testing mass, the kilogram mass, will want to come to the first one, to the creating mass. So someone will have to do that work. And as you are the one who will have to do this work, that's why this magnitude will always be negative. Having said that, let's calculate the different potentials. The first one, potential caused by the first mass, equals negative g multiplying the first one, 5 kilograms, divided by the distance from point P to mass A. This distance that we are obtaining it using the Pythagorean theorem, distance squared equals this leg squared, 4 squared, plus the other one also squared, 3 squared, which is 25. And the distance will be the square root of 25, 5 meters. 5 meters. Okay? The second one, negative g, multiplying the creating mass, in this case, 10 kilograms, divided by the distance, and the distance is this one, 3 meters. And the last potential, negative g, multiplying the creating mass, in this case, mc, 20 kilograms, divided by the distance, 4 meters. 4 meters. And now it's time to use the calculator. If you did it carefully, hope you obtained negative 1.78 times 10 to the negative 10 joules per kilogram. And it is negative. Of course it's negative, because if we have 1 kilogram here and we try to move it to the infinite, we will be the ones who will have to move it towards the infinite. You will have to do the work. It is usually said that an external force must do this work. That's why it's negative. Every time you're working in physics, it is very important for you to explain where does a formula come from. So let me take 5 minutes for you to explain where does this formula come from. Perhaps you are asked in your exams to do it mathematically, so don't forget the things that we are doing. Look, as I told you, the gravitational potential is the work that must be done to move 1 kilogram of mass, a mass of 1 kilogram, from point P to the infinite. Okay? And how are we calculating it? As you already know, work is force multiplied by displacement. Force multiplied by displacement. But here we are doing it in mathematical form, which means using an integral. An integral from point P to the infinite. Always the original point at the bottom and the ending point at the top. Force, vector force, multiplied by differential of displacement. This is the setting. Now let me draw the situation. We're moving 1 kilogram mass from point P to the infinite. This is the way. This one is our 1 mass kilogram. And the first thing I want to give you is that this is the force that our mass is experiencing, because this mass wants to go back to point P and furthermore. And as we are moving it from point P to the infinite, this is the displacement vector, differential displacement vector. And as you can see, the angle between them, they are forming 180 degrees. Why are we drawing this situation? Because, as you probably know, the scalar product, the dot product between two vectors, is defined as the magnitude of the first one multiplied the magnitude of the second one multiplied by the cosine of the angle between them. And of course, the cosine of 180 is -1. Second step done. Now it's time to use Newton's gravitational law to have an expression, a mathematical expression for this force. So let's do -1 and the integral from point to the infinite. The force, there comes Newton's gravitational force, G, multiplying the creating mass, multiplying the test mass, 1 kilogram, the mass that we're moving, divided by the distance squared, the distance to point P squared, r squared. And the differential of displacement, and we are doing these constants will be here, -g, multiplying the creating mass, and the integral from point P to the infinite. And it will be better for us to write 1 divided by r squared as r to the -2 in order to solve properly this integral. Now there comes -g multiplying the creating mass. And can you solve this integral? It will be r to the -2, r to the -1 divided by -1. R to the -1 divided by -1. And there comes the Barrow rule. Okay? This is a mathematical treatment that you have to deal with. We can remove these signs. And now it's time to, let me do it here. G multiplying the creating mass. And as you probably know, r to the -1 equals 1 divided by r. Okay? Between P and the infinite. And there comes the final result. G multiplying the creating mass, and okay, 1 divided by infinite, minus 1 divided by r sub p, the distance of point P. And there comes the final result. This is 0, and we have -g, creating mass, divided by the distance. Let's say that r sub p is the distance, and this is the expression that we have. Please don't be scared by this mathematical treatment. I know it's awful, but as the gravitational potential is so easy to calculate, you can do these calculations, but as an appendix, you can write this mathematical demonstration, and your answer will be more powerful. So please, do it.
Binnacle Project.
Now it's time to calculate section C, where they're asking us to calculate the force experienced by a 2 kilograms mass. So this is the first time, this is the first moment they are placing a new mass here, a test mass of 2 kilograms. That's why they're asking us to calculate the force that this new mass experiences. And only when a mass exists, it is reasonable to calculate the force it experiences, okay? When there is no mass, there is gravitational field, but when there is another mass, there is gravitational field, of course, and a force. And in order to calculate the force that our mass experiences, we could proceed as we did at section A. That is, let's first of all apply the superposition principle. Let's calculate the vector PA, then let's calculate the unit vector, then let's use Newton's law of gravitation in order to calculate the magnitude of the force, and finally the vector force. But as we have already calculated the gravitational field at point P, it will be very easy to do this because we only have to multiply our testing mass, our 2 kilograms mass, by the gravitational field at point P, and that's it. So please don't forget what I'm telling you. It would be legal if you want, first of all, calculate the force experienced by our mass due to the presence of the first one, and the force experienced by our mass due to the presence of the second mass and due to the second of the third mass. It would be a very long way. We would obtain the same as using this other way. Just multiply the testing mass, 2 kilograms, by the gravitational field that we built at section A. And here you have it, 2 kilograms multiplying the gravitational field vector, negative 9.41 times 10 to the negative 11 I minus 8.21 times 10 to the negative 11 J. And we will obtain the result. If you did it carefully, please stop the video and try to use your calculator. Have you obtained negative 1.88 times 10 to the negative 10 I minus 1.64 times 10 to the negative 10 J. And this is the vector force that our mass experiences, perhaps something like that. This is the vector force, the force vector. And it would be also very useful to express its magnitude. Section C, over.
Binnacle project.
And now it's time to finish our problem by calculating the gravitational potential energy. Please don't confuse it with gravitational potential. Now that here appears a mass, we will calculate the gravitational potential energy that it has, okay? The gravitational potential energy, that we can represent it as potential energy, we can proceed the same way as we used to calculate this one, using this formula that you can have access to it at the link that I leave you at comments box. Negative G multiplying the creating mass, multiplying the test mass, divided by the distance, as we did in section B. But as we have already calculated the gravitational potential at point P, we can proceed this way. Just multiply the testing mass with the gravitational potential at that point. And that's it. Again, don't forget what I'm telling you. You could calculate the gravitational potential energy that this mass has, calculating the gravitational potential energy due to the presence of this one, using this formula, calculating the gravitational potential energy due to the presence of this other one, using this formula, and calculating the gravitational potential energy due to the presence of this mass, using this formula, and add the three results up. But as we already have the gravitational potential at that point, we only have to do 2 kilograms multiplying negative 1.78 times 10 to the negative 10. And that's all. If you did it properly in your calculator, hope you obtained negative 3.56 times 10 to the negative 10 joules. Only joules, not joules per kilogram. And I tell you that you would obtain the same result if you did it using this formula for every one of our masses. I challenge you to do it in order to obtain this result.
Binnacle project.
In this video, we've worked with 4 critical magnitudes in gravitation: gravitational field, gravitational force, both vectorials, gravitational potential, and gravitational potential energy, both scalars. Don't forget how we calculated them and how we treated with them, because it will be very useful for the rest of the topic. And as always, for my part, it's been a very big pleasure to be here with you. If you have any doubts, please leave them in the comments box. See you in the next video. Bye! And now, watch a theory video if you think you've gotten lost in some aspects, or skip to the next exercise to continue climbing. And as always, like, turn on notifications and comment. See you soon!